Hello, everyone. Welcome to our first ENVS speaker series of the semester. We have printouts of the schedule for the rest of the semester. If you'd like to take one, they're on a blue paper, red's pointing, on the snack table. Our speaker or our talk next week will not be open to the public. It's just going to be for students. So students, please come. We're going to be talking, or we're going to have a panel of students who did work over the summer, and they're going to talk about those experiences. If you're not a student, I'll see you in 2 weeks. Okay. Our speaker today is Karlee Prince.
Hi.
She's originally from northern Wisconsin. She majored or did her undergraduate degree in environmental geoscience at Northland College in Wisconsin. She then did a master's in geology at the University at Buffalo and is now in the final stages final stretch of her PhD in earth science, also at UB. She can do a headstand.
Working on the handstand.
She will do that after the talk.
Yeah.
And I heard she can dunk. So take it away, Karlee.
Rumor. Hi, everybody. So my name is Karlee, as Michaela introduced me. I want to thank you guys for bringing me down here and allowing me to talk to you about my research. And I'm excited to do so. I think it's pretty sweet research, not biased at all. And the work that I do is going to be focused on something called relative sea level and glaciation history up in Northwest Greenland. And we'll break that down. So this picture is from my last field season in 2024 up in coastal Western Greenland. I tried to bring in a couple field pictures because it's a stunning, stunning landscape. So this is me and my colleague Ola Beneke here in our little Zodiac taking a sediment core off the side of this very foul-smelling marine embayment. It was crazy. And here we have some like icebergs out that kind of dot the landscape up there. So I'm going to click one more time in here. Yeah. So I'm a glacial geologist, hoping to get a PhD next year in glacial geology, which means I study particularly I study the North American ice sheets. So throughout my undergrad and master's degree, spent time on the southeast sector of the Laurentide ice sheet, also in the Lake Superior region of the Laurentide ice sheet. And I also did a stint on the western coast of the Cordilleran ice sheet. I won't be talking about those places today, but if people have questions after the talk, feel free to come up and ask if those are any of your study areas. But today, and during most of my PhD, my work has been up and around the ice history of Greenland. So a glacial geologist who studies ice sheets, my main goal is to reconstruct the size of ice sheets through time as they get bigger and smaller as the Earth goes through natural fluctuations in climate. So that looks like this map here, with the black outline being what the size of the Greenland ice sheet used to be, say 20,000 years ago, to getting smaller around 14, to getting smaller, that's around 8,000 years. And so glacial geologists get to reconstruct how this ice sheet waxes and wanes through the last 2.6 million years, which is the Pleistocene. The reason that we want to know about ice sheets is because there are two of them on Earth today, the Arctic and Greenland ice sheet, and they are the main contributors to global sea level rise right now. And so this graph here goes from 1950 and is projected out to 2100, and it's trying to estimate just how much sea level rise we might see globally based on the melting of ice sheets. And so there's a considerable spread. That spread comes from both, we don't know how much carbon we're going to emit yet, but it also comes from we don't know exactly how ice sheets respond to warming. We know they melt, but how fast and from where? And so those are some of the questions we try to ask as glacial geologists and why we do what we do. So not sure how familiar if anyone's taken a glacial geology class, but I thought I'd detail the last about 20,000 years of climate history. So here we have on our x-axis, we have time back to 20,000 years ago to the present on our left. And then we have this delta 018 record, which is isotopes that are recorded in the Greenland ice sheet. You can interpret this as when the high values are higher, it's warmer, and when they're lower, it's colder. And so here we have our last ice age, the last glacial maximum, as a steady state here. And then during what we call the bowling Alarod, you get a really rapid rise in temperatures around the Earth. or that's most specifically the northern hemisphere in this graph, but you can use it as a proxy for most of the world warming. And then a cooling event we call the Younger Dryas, and then a warming into what is denoted as the Holocene, 11,700 to the present. And so in this last 20,000 years, we have a couple times where we can look at warming events that would tell us how the ice sheet responds to warmth. So for example, if this is the ice sheet 20,000 years ago, and this is the ice sheet 14,000 years ago, that gives us a sense of how fast and from where the ice sheet lost mass due to this amount of warming, for example. Take it again. This is technically 8,000, but if you squint, we can imagine the change is right around 11.7. And so that's kind of a little more detailed version of why we care. And also, this is going to help us if we think about the future. So if you can take this probably greatly exaggerated line, I'm not an isotope geochemist, and we envision a warming into our future, just how small is that ice sheet going to get? What's the sea level equivalent? Those kinds of questions. And so glacial geologists work on tracking. So just how do we get these ice sheet histories, right? How do we show how the ice sheet changes through time? And as glacial geologists, we get to go out onto the landscape and use what I phrase indicative deposits to show where the ice sheet used to be through time. So in this figure, what we have is the Greenland Ice Sheet as that big white blob. And ice sheets are really good conveyor belts of all of the debris that they grind up at their base, and they bring them to the toe of the glacier and they deposit it there for a long time. So if the glacier is sitting in one spot for a long time, the pile gets really big. And then as the climate changes, it gets warmer, that glacier retreats and it leaves behind that pile and the outline of what it used to be. And so really fortunately for us, those are all over the place in Greenland, and they are usually continuous in some places where you can track just the size of the ice sheet. And then I won't get too much into the geochronology side of this, but we have quite a bit of tools in our belt that we can use to tell when these ridges were formed. So for example, then we can assign an age to an outline, like 2,000 years here, 1,000 years here, and like 200 years here, for example. And that allowed this compilation in 2024 by Karlee Prince to map out the history of the Greenland ice sheet from 14,000 to 7,000. So each one of those kind of clown colors is a different extent of the ice sheet at a different time. So you can see it getting smaller and smaller and smaller. Sweet. That can be done with a lot of like terrestrial glacial geology techniques. And that's really helpful, but we've done a really good job. There's plenty of uncertainty there, but we kind of are approaching the time where we need another avenue to get at some of the younger ice sheet change. So you'll note that this scale goes up to around 7,000 years ago, and that's about when the ice sheet got to its present formation, and then it has re-advanced back out over some of the areas that it had previously deglaciated into its present form, and so we don't know how small it was during this last 7,000 years. And so another way that we can look at this is through glacial isostatic adjustment. So this figure just shows a cross-section of our Earth, and the idea of isostasy is that you have a crust that is lighter than its mantle, and so it's bouncing, or it's in isostatic equilibrium with the mantle, and so you have a crust that's kind of floating on a squishy mantle. And I think about glaciers, so this is glacial isostatic. So we're thinking of how an ice sheet would load the crust, which could then sink down into the squishy mantle, which causes the mantle to flow away. And so in places where we used to have large ice sheets, you get depression or subsidence, and in the periphery around it, you get what's called the forebulge. And this is helpful for us because the amount of ice that grows over a spot proportionally subsides an area, which then will rebound a certain amount based on how much ice there used to be. So it's another way that we can map out how much ice there used to be in different places. And so some of the techniques and the measurements that we can make to track what the crustal movement is from the ice growing and shrinking is a term called the marine limit. So in this schematic, we have an ice sheet that is terminating into an ocean. The ice sheet leaves, and that brown crust is isostatically pressed down into the crust after the weight of the ice. And when that ice leaves, the ocean is able to inundate as far up as it can for whatever the water level is. And they call that the marine limit, how far inland it gets. And then after the ice sheet is gone, you have a steady water level, and your land rebounds relative to that ocean. So that's the relative sea level is where it used to be. And so along its way, it creates all these deposits. Boom, 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 boom. And that happens if you are in a near field area where you had ice pushing down on a spot. The reverse is true for a forebulge area where you were actually uplifted when the ice sheet was bigger and has since sank back down. So you can kind of think of this schematic in the opposite, where you are higher than sea level and you've only fallen down into it and sea level has ingressed. And so a map of that in the Northern Hemisphere looks like this, where all the areas that are blue are places that have been subsiding or that were subsided and have been rebounding since the last glacial maximum. And then those blue or the red contours show where we're uplifted during the last glacial maximum and have since fallen back down. So that's kind of a map of the forebulge. That's going to be important for later. This is what it looks like when you have rebound on a landscape. So this is a bunch of raised marine beaches. So if you've been to like the ocean and you see like coastal geomorphology, that's all being deposited as an ocean is at that coastline. But if that land is rising, it all gets abandoned and it gets raised up and preserved. And so you get to go to a landscape and you can pick through all these little beaches and they indicate that the sea level has been falling or the land has been rising. Those are the two movements. Another thing that we can look at are raised marine deltas. So same thing, you have a river flowing into the ocean and it has a delta that is out into the ocean. And then that land rises and the delta is abandoned and raised up. And then you can get a series of these, boom, 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 all the way down to the present. And glacial geologists, I'll get a little bit into dating now, or actually raise a hand. How many people know about radiocarbon dating? Where are we at? Pretty good, okay. So for example, if you have sea level that is higher, you have marine bivalves that like to grow in these sediments. And when they're alive, they're in equal exchange with the atmosphere, they're eating up carbon. And so they're getting, this schematic is a tree, but hold with me. You're getting the amount of carbon-14 that is naturally produced in the atmosphere infused into its like tissues in its shell. And so when it dies, that infusion cuts off and radiocarbon, the carbon-14 is radioactive. So it's going to decay at a constant rate through time. And you can measure the amount of carbon-12 to carbon-14 to tell how long ago something died. So if we deploy carbon-14 dating to all these different shells, we'll get ages for where the ocean used to be. We can also do that with lake sediments. And so in this example, instead of we have natural basins in the landscape that were once below a certain sea level that then are brought above sea level, isolated from the ocean, and then go from being a marine basin to a freshwater basin. And if we take a sediment core from one of these guys, the sediment will look like marine sediment with marine indicators to freshwater. And we can use radiocarbon dating to tell when. And so this is an even better way to track sea level because it tells us exactly where sea level used to be. So we call these high quality data or sea level index point, which is where these slips are, but we'll just stick to high quality. Okay, so for example, that would look like this is your landscape, this is the modern ocean, this is a lake that's the highest on the landscape, another lake a little bit lower, and then maybe you core this one down here, and that allows you to track sea level fall through time. Okay, so that kind of work has been done around Greenland quite a bit. So all these red triangles are areas where you had that low quality data. Those are shells. They just tell you that the ocean had to be somewhere above it for that shell to be living in marine sediment, but they don't tell you exactly where sea level was. Whereas those circles tell us this high quality data. These are isolation basins, or what those are called, basins that are isolated from the sea. And those are spatially less common. And from this data, we can create these kinds of maps of, this is the marine limit, but it's also a proxy for ice height. And so it can tell us past times where there was a lot of ice in Southwest Greenland, a lot of ice in East Greenland, and a lot of ice in the north, indicated by these high values. But for some reason, we're getting this low value along Northwest Greenland. This also happens where no one's done any work. And so that is what I'm going to talk to you guys today about, is this Northwest Greenland story, what's going on. What's interesting is that you can see that there's a really similar amount, there's a really similar distance from like the ice divide somewhere in the middle of Greenland to the continental coast in both Southwest Greenland and North Greenland. In fact, it's even farther out up here. And yet it has a lower value of why the ice was like, it has a lower value of a marine limit indicating the ice was not as high as on first analysis. So that's another question we're going to try to dig into. Well, it's a spoiler. Oh my gosh. Okay. So this is where we went. It is the island of Apilitok in North Greenland. So maybe I didn't point that out here. This box here is where we're going. Into this northwest Greenland. There's a lot of these fjords. And so we went to the island of Apilitok, and this spot was good because it has lakes that are close in elevation to modern sea level, and it also has some of these marine basins that have kind of like skinny, what we call sills here, that are places where it gets shallow and then it gets deep again, and that could have hosted freshwater lakes if sea level was lower. And so we had the opportunity last summer to fly out there. We get to fly around in these twin prop planes that are super sweet over these really beautiful icy waters. We got chartered from the larger town of Upernavik out to this island of Apilitok by our friend Jan, who smoked cigarettes the entire time he drove us out there, had like a cigarette in one hand, was like driving the boat in the other, and we were like, duh. But he had navigated these waters for absolutely years. And then once we get to the landscape, we get to haul all of our gear everywhere. And so this is us carrying some of our boats from lake to lake. Here I'll say another huge thank you to my field team. And here's us just carrying the motor back and forth. We had a whole outboard motor that we carried over. It was crazy. And then once we get to our field site, we set up shop in our boat. We send down a piece of polycarb that has a piston at the bottom of it. That's going to act as a suction. And then we have a hammer that pounds the polycarb around our suction. And then when we are done coring and we have mud in the tube, let's see if this works. No, it doesn't. This is a little video of us of rocking the boat back and forth, which is how we unstick the suction from the bottom of the lake. And then the sediment core on deck, and our field team is happy. And so we had a successful field season, and we got the bathymetry maps of these 3 marine embayments, and we collected cores from 6 different basins. So these values are elevations above sea level, and then these are the sill depths below sea level. And some of the cores look like this. They're very beautiful. The top one looks like a plank of wood or something. These are all laminations, really micro scale sedimentation differences in anoxia maybe. And this one has another layer of laminations, and then some of this like really coarse, chunky stuff. And this one even has deglacial sediments in the bottom. So this blue flower is really indicative of glaciers in the catchment. And so my job is to take these sediment cores back to the lab, and I take out centimeter wide sections and I sieve them underwater, and then I go underneath a microscope, which you guys can come after the talk and look at, are the macrofossils left behind. And when I'm in a freshwater section, I can find things like a lot of water, a lot of insects, unfortunately for me, who's not really an insect person. It's mostly like legs and antenna and eyes. It's freaky. But so we get these things like these head capsules. My favorite one are these caddisfly larvae, which make the shell of their like larvae butt out of rock. And so these are left behind, and they're really pretty. And then the eggs of another common water flea are often left behind. These are all telling me that the water above, the water in the basin at the time of this deposition is freshwater. Whereas when I get into a marine section, I can find things like foraminifera, which live in marine water. And sometimes I find these pieces of like a jellyfish factory. I'll find this little piece around all the time. And then what are really super common are just algae, just marine algae. And so if I go through centimeter by centimeter, I can create assemblage graphs that have lacustrine sediment or lacustrine indicators on this right side here and marine on the left. And when you go from having a predominantly lacustrine assemblage to a marine assemblage, that tells you that's where the shift in the sediment core is between having freshwater and when the ocean reached the basin sill, ingressed, and allowed marine water into the basin. So that's where we then would target, and some are more sensitive than others. So this one goes from the bottom of the scale here, goes from 0 to 3, 1 being very rare, I only find 10. The second one being common, I find 10 to 100. And then the third one being very abundant, there's hundreds. And so some are more sensitive. So this was fully lacustrine, you get abundant, gone once there's any marine influence. And same thing with this hydroidea, which is the jellyfish, nothing in freshwater, but it does get increase in concentration as you get more marine. The next thing is XRF. Does anyone know what XRF is? So sick. Yeah. You shoot an X-ray, it's called X-ray fluorescence, as XRF. You shoot an X-ray at the sediment surface, and it excites the atoms that are in the sediment core. And as that energy is leaving the atom, it lets out a wavelength that is specific to each atom. And so you can get like or to each element, excuse me. And so the elements come back as like an elemental abundance through time. We can make graphs like this, where this is telling me how much sulfur there is through the core and how much bromine there is in the core. And then you can take ratios of those two things together, like calcium to titanium, to find how one is varying relative to the other. And these are helpful because we expect more calcium, for example, to be in ocean water than in fresh. Same with bromine. That's much more common in ocean water than it is in fresh. And sulfur usually is higher in marine, but in our case, in these lakes, we get it higher in our freshwater sediments, which we think is something going on with the terrestrial erosion cycle. And so this is kind of our backup. We use these two things in combination to find where the isolation is, and then we use radiocarbon dating of terrestrial macrofossils in these intervals to tell us what time this sediment core was ingressed or isolated. Good. So both results that we find in Epilatoc. So starting with the lowest sill basin, we're going to start in this little basin here and then work our way up to 4, 1.5, and then we'll talk about the today lacustrine lakes. So this one, for example, is our lowest basin. So here we have, and this is also the one that I think I had in the example. So we're pretty familiar with this core. Glacial at the bottom, this is that blue silt. And then I find lacustrine indicators of high sulfur, but low bromine and calcium to titanium until around 5,000 years ago, when we get an uptick in the calcium to titanium ratio and the bromine, which is associated with a change in the macrofossil assemblage. Cool. So here we find the ocean ingressed into a freshwater basin around 5,000 years ago. In this example, at 4 meters, this is my favorite core. We'll talk about this one a little bit. Here we have lacustrine sediment at the very bottom, indicated by low calcium, low bromine, and high sulfur. And then we get this little interval where the calcium really peaks. Bromine's like a little bit high. And then eventually we get this kind of really rapid sedimentation. You'll see the radiocarbon ages are all the same through this interval. And then a big increase in the bromine and the calcium, full marine conditions. So we interpret this, and then our macrofossil assemblage agrees. We have lacustrine sediment at lacustrine indicators at the very bottom. We have a mix of the two through an interval, and then lacustrine kind of drop off, and the marine get really common. And I'm going to take you through this graph here. So this graph has the bromine and the calcium to titanium, bromine in blue, calcium to titanium in green. And so we're going to start at the very bottom where we have low values in what we think are lacustrine sediments. In this lake here, this is the fjord system. This is where our sediment core is from. We're interpreting the ocean to be lower than the elevation of the lake. And so this lake is draining over this outlet into the fjord. And the cross-section of that is you have your ocean out here, you have your freshwater sediment in this lake, and it's depositing freshwater sediment, or freshwater and the freshwater sediment. And then you have like a channel connecting the two that's probably full of like debris from the landscape that's washing down into the ocean. The next step that we have is really high calcium compared to titanium in a few marine macrofossils. And what we interpret this as is the very, very highest tides during the year are able to come up into the sill, and they deposit, or the marine water is a little bit more dense than fresh water, and so it sinks to the very bottom, and it brings with it some floating marine material, but it also creates an anoxic zone at the bottom, which then preserves laminations. And something that I don't know yet, that I'm still investigating, is causing calcium to be really high in this interval. If anyone knows why, please let me know. And then we get this really fast deposition of these sand layers, or really fast deposition, excuse me, and this is associated with sand layers and a lessening of these laminations. And to us, this is now these highest tides really reaching the lake like much more often. And they're able to scour some of these channel sediments and bring with it these kind of big sand deposits. And so then you get these big layers of sand and it's depositing really, really fast when it's like kind of like tidal over your sill. And then finally, our bromine and our calcium and titanium are very high. Our sedimentation rate slows back down. And then this sediment core has this like really chunky, really rich macrofossil rich section that is like full of the scariest things you've probably ever seen. And then that is a fully inundated fjord, and we now have marine deposition everywhere. And so our sediment core that we pull out of the bottom looks like that. And so that's a really fun core, because you can really get like a couple phases of sea level rise out of it. The last core that we took was from a still tidally connected basin, and we kind of overshot the top. And so it's mostly lacustrine, and the sea level inundation is in the very top 2 centimeters. We think we caught it. We can't see it in the XRF, but we got some marine macrofossils. So we're, a little less, well, and we also get it in the coarse deposit. So this is MS is a proxy for coarseness. So there's more sand in this top and some marine macrofossils. So we're feeling pretty good that we found the inundation of this basin as well. And so then we can plot this through time as a relative sea level curve, which then tells us the rate of sea level rise through time between these basins. And so on this graph, we're going, sorry, I apologize for switching axes sometimes, but now we have today on our left and back to 12,000 years ago on our right. And I'm going to plot freshwater sediment as this tan and marine sediment as this darker brown, and then some of our radiocarbon ages that tell us if sea level was lower, if sea level was higher, or if it was right at the elevation of our lake. So our first sediment core from the lowest spot, we have our contact right below this rock here. And so our radiocarbon date there says around 5,000 years ago, the ocean ingressed into this basin. We'll pop up to the next one. This one has the ingression point around 15 to 1600 years ago. My next step is to add a couple more of these dots in here, because I think I'm going to connect highest astronomical tide and mean sea level in here and see how that looks. And then finally, our most recent basin has ingression only about 800 years ago, which is kind of cool. Timeline of like people who had probably lived there. And so then all of the lakes that are above the ocean, which we carried all of our boats everywhere to get to, had 0 marine sediment in any of them. And so that was really fun for my field team after I split these cores. And so we can draw a line through these curves that tell us that sea level has only risen in this spot in Northwest Greenland over the last 12,000 years. Pretty sweet. This is also very surprising, and the only known occurrence of sea level rise around Greenland that we have documented so far. And so if I can take you back to this map and some of the thoughts we were having at the beginning of the results discussion about why we have this low marine limit right here, even though the ice was all the way out to this Baffin Bay ice shelf in here. It's a little confusing. You'd expect there to be a lot of ice sitting over this spot. You would expect there to be a lot of rebound. And so finding sea level rise is pretty exciting. That means that instead of the weight pushing the crust down, which then popped up, it means that this spot around the ice sheet was higher than higher during the last glacial maximum and has only been falling. Anyone know? Anyone have an idea of what we might have found here? As it was a spoiler from the beginning. We think that this might be a spot that the forebulge had uplifted even in Western Greenland, and that we've only found the crust falling. And it's really surprising that we find it here. And we don't think it's the Greenland forebulge, but instead we think that if you're thinking about these 2 ice sheets sitting on a waterbed, I meant to say that earlier, waterbeds are a great example of GIA. If the Laurentide ice sheet is sitting on the same waterbed as the Greenland ice sheet, it's like you have an elephant sitting on one part of the waterbed and like a small little like mouse curled up next to it. And so the mouse is competing with the Laurentide ice sheet for the weight pressing down. And so map of where the Laurentide is, you see that there are really high values through this Baffin Bay, meaning that the forebulge had been funneled up and was rising the crust all through Baffin Bay. And we think that the weight of the ice overlying this part of Greenland, while still thick, was not enough to outcompete this mantle forebulge. And so it's the forebulge was uplifting, there's a little bit of subsidence that would be coming from the ice sheet, but this is winning. So the land is rising. And then once the Laurentide starts to shrink and the Greenland starts to shrink, it gets to fall back down. And so we're capturing that signal. I didn't realize this one was on here. This is predicting what ice sheets. So if you give an ice sheet history from like an ice sheet model to a GIA model, which would then predict what the vertical land motion will do given a certain ice sheet history, you can plot it at the same time as your data. So on this graph, those two blue lines are two different model predictions of what the sea level should look like. And they are conflicting. Neither one quite get it right. One of them says there should be rebound first. The other one says it should be rising much faster than we get. And so that kind of goes to show just how important getting field data is to constrain some of these models, because now we get to tease out what the ice history is. And also what I haven't got into is what the Earth parameters are beneath the Earth, which has also has a big influence on what the kind of sea level history you get. And so this is some preliminary model output, forgive me, it's blurry, from a colleague of ours who has taken the Greenland ice sheet like out of his model and then put it back in to see the influence of the ice sheet's weight on the crust. So this is another way of looking at this one without the Greenland ice sheet. This is purely the four bulge shape with just Laurentide loading, and you can see all of Western Greenland gets uplifted. And then you add the ice sheet back in, and you can see that places in Northwest Greenland, East Greenland, Southwest Greenland have enough ice to overcome that, but we're modeling that we would get uplift in Northwest Greenland. So that was cool to see that we're agreeing with some models. And that was actually the output shown here, this one that expects more outlet or more subsidence than we show. Okay, great. That's the talk that I have for you guys today. So there's some fun waterbed movements going up in Northwest Greenland. And I'm excited to answer any questions that you guys have. Thanks. Sounds good.
Those sediment layers look really clean. You don't have like bioturbation going on with worms digging things through up and
Oh, do you want to go in front of the microphone? Thank you.
Straight up. So this core, for example, if you can see, maybe if I go back two more, it'll be more clear. So this core has lacustrine sediment beneath that blue dashed line. And there's that interval where it's quite gray right in the middle and all those red lines across it. Those are aquatic bryophytes, and those will bioturbate. And so the layering through that section is kind of massive, we'd call it. It's 1 or 2 centimeters wide. And that's the result of the bryophytes kind of like mixing. Actually, wait, I have a better one. This one. This one has laminations at the bottom, pretty massive laminations that's a little bit darker. And that one has really small bryophytes in it. And then as you get higher up in the sediment core, it becomes that like just like massive, chunky, there's no layering up in that bright section. And that's just like bryophytes kind of moving sediment around everywhere up there. And so that's common in the lacustrine sediments. And then once it's fully marine, I think that's also pretty common. So like this core, for example, up in this side, what you can see is there's no layering structure either. So it's also probably bioturbation. And then luckily for us, when the transition is happening, often you get anoxic bottom waters that would decrease the bioturbation because nothing can live down there. And that allows for sedimentation to preserve those fine sediments.
Just out of curiosity, kind of on the same topic. So like when you're looking at the layers, is that what you're doing like under the microscope, or and then you're doing it like centimeter by centimeter? Like how long would that take to do that like full bar?
Mm-hmm. Okay. So no, we'll go this one. So it's about 40 minutes a slice is what I've found for myself. So I'll take a centimeter of the core. I usually take the whole core out, and I'll put it into a sieve. Then I have 3 sieves that I sieve the sediment through with deionized water. And so you're trying to break up the macrofossils the best you can with the water. And then if it's still pretty clumpy, you lightly sieve it with your finger to break it up. And then I put that into 3 little petri dishes at different size fractions, and we'll count what I find in those. And so that, yeah, and then you get kind of into a rhythm of what you're looking for. Sometimes you'll find on one of those, I'll put red tape on the bottom, so I split it up into like quadrants, so I can count what is in one corner and then compare it to what I find in another corner. And that makes it go by a little bit faster because you get like a representative sample. And yeah, and so then it's really just like looking down through the microscope, which you'll see over there at what I'm finding. And so I've spent between this field season, which had 3 cores that I've done this in, and then my last field season had 8. It's been a lot of time sieving and looking at the microscope.
Thank you.
Yeah.
Thanks for a great talk. Could you say a word about the relevance of your work for Greenlandic archaeologists?
Yeah. So there's a spot. I have another. Thank you for the question. I have another study site in Northwest Greenland, and that has these pre-Thule occupations. So there's like houses and stuff that date to a time period that they consider like the Thule period, and those are kind of cool because you assume that they would be living right next to the ocean. And so it shows that like their dwellings start at like a higher elevation than what the ocean is today. And then the younger ones get even closer and closer to the ocean. So that's kind of fun. The significance could be that you find in places, most places around Greenland have sea level fall. And so if you were fishing in some areas, for example, which is like one of the main exports and sustenance things that they do up there in the summertime would be fishing in open water. The basins are changing through time. And so you're always kind of like, is my great-great-grandson going to be fishing in the same place or not, for example? Because that might be isolated and become brackish and then no longer have the fish anymore. As in today, going into the future, I have some colleagues that work at Columbia that have mapped out some of the ports that a city called Ossiot uses that have quite shallow sills going into where the main amount of traffic goes in and out to go fish out in the ocean and then come back home. And those are projected to be becoming terrestrial, like the sill is rising and it's going to cut off from the ocean because Greenland today, losing as much mass as it is rising like pretty rapidly. And so a lot of the bays and ports that are within 5 meters of water depth could become lakes, which would impact a lot of the fishing communities. Yeah.
Great talk, Karlee. I have a broad question. How much do you have to think about ice shelves when you do this kind of work? Does it matter very much, or does
Ice shelves?
Yeah, ice shelves.
Good question. I haven't thought about ice shelves that much. So you're kind of thinking about you have a landscape here that's deglaciating, and maybe it's beneath an ice shelf for the initial sedimentation kind of thing, and then ice shelf breaks up, and then it's under open water conditions and then pops up.
Sure, or the ice for the GIA stuff, if the ice shelf is buttressing the ice sheet,
Yeah.
right? It seems like that might matter.
Mm-hmm. So we're thinking about that. So I don't think it matters in terms of weight, right? Because that ice shelf is already, the weight is going into the ocean. It's already compensated for. So I don't think if you have an ice shelf, for example, you're going to like you will create like thicker ice because it can be buttressed, which would then cause like more rebound afterward for sure. Another reason that we're confused that we don't have sea level fall here because there is new evidence for this Baffin Bay ice shelf. Something that we've been thinking is a little off topic, but it has to do with ice shelves, so I'm going to take it. Something that's kind of exciting here is that if we're finding that the forebulge was beneath this Northwest Greenland shelf here, that would mean that during the initiation of ice sheet growth, you would be getting the mantle funneled in front of where an ice sheet is growing out onto. And so you have land rising, which then allows the ice sheet to grow even farther. And so it's like a a positive feedback for ice sheet growth during the beginning of a glaciation. You can allow it to grow even farther out, which, depending on how much the spore bulge was rising, could be playing into how that ice shelf even formed in the first place. And then you have the reverse during deglaciation. So now all of a sudden the spore bulge is falling, and not only is this marine terminating ice sheet being hit with warmer water, rising sea levels, the land beneath it is also sinking, making the sea level rise even faster. And so then you get really rapid deglaciation, which is what you find actually in Northwest Greenland. Is it's one of the earliest places to deglaciate. And so where the ice shelf, think about ice shelves in that way.
Cool. I have more questions, but I'll ask you later.
Nice.
Anyone else? Okay, thank you very, very much.
Great. Thank you guys. Good talk. Oh, I gave a quick talk to do this. Thank you. So if you guys want to spend the next 10 minutes before you gotta get to your next class, I brought a sediment core from Greenland. It's the sediment core that thank you. It's a counterpart to this one that has the fun ingression story. So this one's taken from the same depot center, but it's a little bit shorter. This one I would bring, but I've like demolished the core, so you can't see anything. So if you want to come by and look at that, you can. You can feel the sand layers if you want to. Just don't like stick your fingers really deep in it. Just lightly touch. And then underneath the microscope, what we have are two petri dishes. One has the marine fauna that you can look at. There are foraminifera. There's algae in there. And then I have a freshwater one that I think has a caddisfly larvae in it, and probably a lot of bug bits. So feel free to come up. I'll be over there if you have questions.